We've got quite a bit of things to cover today, so the sooner we can get going, the better it is for you. Not just me. Some things we're going to be doing today. We're going to have a mini quiz on concentration. We're going to save that for the end of class, though. It seems to work out better today. We're going to talk today in our notes about solubility curves, which is what your lab was about on Monday. So this will tie in really nicely, hopefully help make sense of what it is that you were doing on Monday, and kind of help you a little bit with that. And then at the very end, before we take the quiz, talk a little bit about the lab and how to do the lab write-up, especially the post-lab.
Where's Mr. Gussie?
Mr. Gussie is currently probably instructing people on how to play tennis really successfully. Tennis meet today.
But he's instructing how to do it well?
That's the whole.
That's just for real. Hey, you know,
Mr. Gussie's probably ready to stuff.
whatever, man.
Mr. Black is out here because he has a sick puppy dog.
I'll give you a sick puppy dog.
Alright, so on your note sheet, you should have in the upper left-hand corner a graph that looks exactly like this. Let's go, people. You should have for those of you that stand at the door for 2 minutes before you're ready to leave class from your previous class, you should be pretty much ready to go at the very beginning of the next class. So on this curve, you're going to be drawing in some stuff. So you've got an empty kind of graph. It looks exactly like this. So what we were trying to do as one of the parts of your post lab for the experiment on Monday was you needed to make a graph. And it shouldn't end up with a nice little curve shape like this from your data. If you did not get that, that's okay. You probably had some errors in measurement, or some people had missed the one of the procedure part that said to make sure that your volume of water that you had added by those 20 drops or so was about 0.9 to 1 gram. So some people were a little bit short of that. Some people were a little bit over that. So that kind of is going to cause some error in your measurement. So if you don't get a nice plotted points that make a nice little curve that looks a lot like this, that's all right. We're going to give you some information, like I said, at the end of this that you can use for doing the post-lab questions. Because if you're trying to use your lab and you've got points going all over the place, it's like a roller coaster looking kind of a graph, that's okay. We'll have that something for you so you can use that to get good answers for your post-lab stuff. Instead, you should draw this little curve in here, because what does that curve represent? On a saturation, you're calculating the saturation, that represents saturation. So that line is saturation, or it's considered a saturated solution at that point. If you do a calculation for how much solute you have and at a certain temperature and it ends up in this pink region, then it's considered to be unsaturated. You could add more solute to saturate that solution. You can get more stuff dissolved. The weird one is, what if you actually had more stuff dissolved in this blue section than what the temperature says should be able to be dissolved there? That's considered supersaturated. Supersaturated is not stable. It's not a stable condition to be in. There might be some solutions that can't be okay there for a little while, but eventually what's going to happen is the water can no longer keep those molecules apart or those ions apart, and they're going to start clicking together like Legos, like little magnets. They're going to come together and they're going to clump together and eventually get like large particles and start to sink down to the bottom. You saw that in the lab. That's what we were trying to do. We were trying to get the temperature to cool down to where you got to saturation. Sometimes you might go a little bit beyond and end up in supersaturation, but by stirring, you kind of help force those ions and those molecules to come back together. And you can see, oh yeah, those little clumps, little white flecks in there. That's the solid starting to come out of solution. It can no longer stay dissolved because it's just not the right temperature for that much to be dissolved. Any questions about that first little graph that you have there? Should have that filled in pretty nicely. Look from the front row. Unsaturated. So unsaturated, kind of an important vocabulary term to have here. Any point below the line. And that's really all you need to write in there. Just a little highlighted part there. You have to write every word that's in that highlighted part. Just unsaturated on a saturation curve or on the graph is any point below that line. It's unsaturated. We got that example is right on your note sheet. If I have 30 grams of salt dissolved in 100 grams of water at 90 degrees Celsius. I look at that, where does that plot out at? Underneath the curve. So that means that this is unsaturated. I could get more salt to dissolve. I could get about another 10 grams, and then I'd be up at that saturation line. So that doesn't mean it's unsaturated. It doesn't have the maximum amount dissolved. I could dissolve more in there. Saturated would be, we're sitting right on the line. So any point that is right on that line is a saturated solution. And it's specific for that amount of solute and at that temperature. So any point on the line represents that saturation point. So again, the salt, if I did put another 10 grams of salt in there, I could get it to dissolve. As long as the temperature stays at 90 degrees, I'm going to get that 40 grams to dissolve it, but that's it. I am at the maximum that it can handle. I couldn't try to get 42 grams in there. The 2 grams would probably sit down to the bottom. They'd just probably sink and they wouldn't even dissolve. So if that's the case, if I couldn't get any more to dissolve, how do we get a supersaturated solution? Well, supersaturation is kind of a special technique, and a special thing that you can do. So here in this example, if somehow I was able to get 10 grams of salt more than that 40 grams of salt, I got 50 grams in there, and the temperature is at 90 degrees, that's supersaturated. That means that those ions are probably going to clump back together and start to sink out of there. But how can I get there? Well, first of all, I need to be able to dissolve that much. So that means I needed to bump the temperature up, probably pretty close to boiling. I got that boiling point up close to the temperature to boiling. I could probably get that extra 10 grams to dissolve. Then if I let things cool down, it cools down to 90, and that 10 grams hasn't had a chance to kind of like clump together yet. Oh, there's my supersaturation solution. Eventually, though, that'll happen. Eventually, those particles will come together. And like I said, some solutions aren't very good at that. Like as soon as it starts to cool down just a little bit, it might be supersaturated for just a few seconds, and then it'll start to form that precipitate, and those solids will start to sink down to the bottom. Some solutions, though, are really good. They can stay supersaturated for a long time as long as they're not bumped or kind of like knocked around a little bit, or anything introduced in that those particles could then kind of build up around and be attracted to and attached to. So we'll watch a video of this, of a supersaturated solution. This is one of the best chemicals at making a supersaturated solution. It's called sodium acetate. That good music goes on. Now, so it said like it's available online. You can buy sodium acetate online, but you can actually make it yourself. If you combine baking soda and vinegar together, and you kind of heat it up, kind of cook it up to kind of drive off the water that gets produced, you can make sodium acetate. That's the combination of sodium bicarbonate and vinegar. Vinegar has acetic acid in it. Acetic is where you get the acetate part. So they're putting it, that's the sodium acetate, the solid into some water. Pure water, distilled water works best. And you're heating it up to get it to dissolve because you're going to get that saturation at a very high temperature. But then you cool it down by putting it they put it in the refrigerator or in a freezer to get it to a lower temperature. That means that now you're going to be at a temperature where there shouldn't be that much dissolved that you get dissolved at that higher temperature. Even though it's at a lower temperature, it still looks like a solution, like a regular solution that could be saturated or unsaturated. And now it says to touch it, and typically that can happen. Like, I was thinking about trying to do this demonstration, and I made some last night, and I put it in the refrigerator over here, and I don't know if somebody must have opened up the refrigerator and closed it in the morning or later at night, and I went back in, it was all solid again already. Because you can just agitate it a little bit just to get enough of those particles to clump together, and then the rest of it just comes out of solution. Won't stay in solution anymore. So they say just to touch it, but they kind of cheat, I think, a little bit. You can kind of see that they have like a little bit of a crystal maybe already on the bottom of their finger, and they put it in there. That makes it go really fast. I think if you were to touch it, it wouldn't come out of solution quite as fast. But this is pretty fun to watch. coming out of solution. Now they call this hot ice. Technically it's not ice because that would mean it's water. That's just sodium acetate now. That's just the chemical. That was the solute chemical. So they also call it hot ice, and it's used in hand warmers. They're going to show that here in the video in just a second because it generates a lot of heat when this happens. There's a video online, LA Beast. I don't know if you know who LA Beast is from YouTube. He puts his hand in a supersaturated solution of sodium acetate and he gets a bad chemical burns. So here they're pouring it out, and there was some crystals down in the bottom of the pan, so as soon as that hits those crystals, those particles can clump around there and come out of solution, and it follows all the way up and starts going back up into the beaker itself. Right, it's going right up in. Make stalagmites or something with it. It would burn you if you just put your hand in it. So that's pretty neat stuff. You can do that at home if you want. You can make it yourself with baking soda and vinegar. All right, so we can kind of shift any solution we want to from being saturated to unsaturated or supersaturated just by adjusting the temperature. So here we have the same amount of solute across the middle here. But depending on the temperature, down here at the bottom, determines whether or not we have a saturated, supersaturated, or unsaturated solution. So if I have a saturated solution, I want to make it unsaturated, I can heat it up. It's still got the same amount dissolved, but now at this temperature, it's not at the saturation point. If I was here at unsaturated, I want to make it saturated, I cool it down to get it to that point, and I got a saturated solution. If you know a chemical that you want to be supersaturated, you can figure out how much you can dissolve at a higher temperature, cool it down, and get it at supersaturated zone. That's how rock candy gets made. By dissolving sugar at a high temperature, you can get a lot of sugar dissolved because the curve goes up. High temperature means I can dissolve a lot. When I cool it down, I get a supersaturated solution. So when you put a string into your solution, then sugar crystals will start to kind of clump onto that and grow and make a really big giant chunk of rock candy. The rock candy is made that. All right, so on the next part here, you need to kind of ignore this, and not worry about writing this down. Just remember that solubility is defined here as how many grams of your solute can be dissolved into 100 grams of water. So whenever you see a solubility curve like this, a solubility graph with all the curves on it, know that that's the relationship. Grams of your solute in 100 grams of water. So at some point in there, there's a spot on your sheet that says like the trends, solubility trends. We have two trends we're going to look at. We're going to look at the solubility trend for solids and gases. So for solids, what happens as we increase the temperature? What happens to almost all of these except for one? Increases. Yeah, the solubility of most solids will increase when you increase temperature. Salt does that. Right? There's NaCl salt. It gets dissolved more as we get a warmer temperature. Sugar is that way. All of these except for one. This guy down here at the bottom. Cerium 3 sulfate does not. It actually loses solubility as you increase the temperature. There's not many solids that will do that. Most solids, the trend is it will increase. But what about gases? Well, gases are the opposite. As I increase my temperature, notice the solubility of gases is going to decrease. So solubility of gases are going to decrease if we increase the temperature. That's why when you open up a soda if it's cold, there's less chance of it like erupting gases out, because at a colder temperature, more will stay dissolved in the liquid. But if you have a warm soda and it's been shaken maybe just a little bit, you open that top, you can get some stuff shooting out of there, because there's not as much that can be dissolved. It's going to try to get out of that warmer temperature solution much more quickly. So when you think about this, this is important when it comes to thinking about things that live in the water. So this is kind of environmental science. Those of you that want to take an AP environmental science next year, you're going to talk about the solubility of oxygen in water. That's a big one. So when we talk about fish, you're going to have like situations where, like, the swordfish comes flying at you and almost impales you. Or this one, I like this one, the fish just like gets shot. I think that's a barracuda maybe, comes flying right out of the water at this guy. Whoa. That's a pretty good one. This one's my favorite up here. This guy gets so scared he jumps into the water. It's like, there's probably more fish in there. And this one, the fish must be so big it pulls him right into the water. And it's really hard for humans to breathe underwater. I didn't know if you knew that, but it really is kind of a challenge. So we'll watch this little video about dissolved oxygen.
The concentration of dissolved oxygen in water is extremely important to the survival of fish. Dissolved oxygen commonly ranges between 0 and 12 parts per million, but it can vary greatly between night and day.
So oxygen can vary quite a bit based on temperature for one thing, but also time of day is an interesting one. Here's one that a lot of people don't realize. If you take a look at the amount of oxygen, during the daytime it shoots way up, gets really high, and then as it gets to be nighttime it starts to drop off. It bottoms out right before the start of the next day, and then it'll go back up again. It oscillates back and forth. And people always wonder, like, well, why is that? And here's the reason why. Fish are going to need to use that oxygen, but they use that oxygen all the time. Plants are making the oxygen during the daytime when light is out and they can do photosynthesis. But at night, why isn't this just staying the same then, or not going up as much as it does if fish are using the oxygen, and the fish will continue to use the oxygen at night? Why does the oxygen go down? And the reason is because, do plants need oxygen too? Yes. That's one of the big mistakes most people think. Most people think that plants only make oxygen and animals use oxygen.
They do.
Plants do make oxygen, but they also need that oxygen too. They make the food for themselves. They still have to use oxygen to burn up that food just like we do. So they need oxygen too. So if you go fishing in the daytime in the weeds, you're probably going to catch a lot of fish, because the fish will be in there because there's plenty of oxygen being produced by the weeds. At nighttime, if you want to go fishing at night and you go back to that same weed bed that you were having success with, you're not going to catch anything, because the fish are gone. They're out of there because the oxygen's getting used up by the weeds. So they want to go somewhere else where there's higher oxygen content. So we talk about oxygen being plentiful and easily well mixed, and we don't have to worry about finding pockets of oxygen. Fish kind of have to. They have to find where is the oxygen located, because there's not a lot of oxygen that can be dissolved in water. It's a very small amount. All right, so we'll finish this video and then we're almost done.
Due to production of oxygen during the day by aquatic plants, especially phytoplankton, the desirable range of dissolved oxygen, or DO,
It's going to be very sad for this fish
is
here.
above 5 parts per million.
He's going down.
Although they can survive short periods of lower oxygen concentration.
He's not breathing too hard, but now, breathing harder.
Prolonged periods
gills are
below
moving.
5 parts per million stresses fish and slows growth. And
And
prolonged exposure to concentrations below 1 part per million can cause fish kills.
all right. So we'll skip this one. And we'll talk about a solubility curve. So we have this graph on your sheet, and there's some questions that go with it. First one is, how many grams of potassium chloride can dissolve at 55 degrees to create a saturated solution? They didn't tell us how much water there is, so we can assume that's probably 100 grams of water. But if they put a different number in here, if they said in 50 grams of water or 200 grams of water, you're going to have to do a proportion to figure out how much that would be, because these lines are always set to 100 grams of water. So be careful when you read those questions. All right, so I find 55 degrees. It's down here between 50 and 60. You guys probably figured that out. Go up until I find my KCl, potassium chloride. That's right there's my saturation line. So now I just go over to the solubility axis, and I look at that. That's probably what, about 43?
43.
That's 42, 43, 44, somewhere in that range. Let's see what we got here. 43. So don't worry if you thought like, oh, I thought it was 42. We're okay with that. We look for a range. Like, if you had said 37, we're going, no, because that's definitely above the 40, so 37 is not it. Or if you said it was in the 50s, no, we're going to mark that wrong. But if you said it was like 44, 45, we're probably okay with that. Well, these are pretty close within a little bit of a range we think is acceptable, we're good to go. Now this one, what would be the minimum temperature needed in order to get 70 grams of potassium dichromate to dissolve? Again, it doesn't say that it's 100 grams of water, but if it was 100 grams of water, it's really nice and easy. I find my 90-degree temperature, or not my 90, 70. I think the answer is going to be 90. That's so 70 I go across until I hit the line for potassium dichromate. Then I go down, what's that temperature? Yeah, it's 90. 90 degrees. That's the saturation point at 90 degrees for these 70 grams. That's 70 grams of salt. Last problem. If 55 grams of sodium chloride was dissolved in 100 grams of water, at 10 degrees Celsius, will the solution be unsaturated, saturated, or supersaturated? So, I look at 10 degrees Celsius, is right here, and my spot is 55 for sodium chloride. Now I gotta go find out where's sodium chloride at. Oh, it's right there. So yeah, we're above the line. Above the line is supersaturated. That would not be stable. Some of those salt crystals are going to start to clump together and they will fall down the bottom of whatever container it's in. So that's the second part. How many grams is going to come out of solution then? Well, it says I have 55. The saturation is about 35. So probably about 20 or 21 grams. There's 20 grams. And that's it for our notes for today.
Yeah.
Good. That's the good news. You're going to have an assignment. There's going to be a worksheet that goes with this after you take your quiz. Shh, guys, quiet please. After you take your quiz, you're going to take your, you should have gotten a little half sheet of paper. That's going to be your scratch paper for the quiz. You can take and recycle that and then pick up a worksheet that goes with this. But what I'd like to talk about next is the lab for Monday. So what I've done is I went ahead and I looked at some of the data that some people were getting, and I kind of stole their data a little bit so I could have a nice little graph that. Dylan, please put the phone away. Dylan, put the phone away, please. I'll leave you showing people stuff. So what I did is I made this graph that has, it's just a table of the stuff that you're supposed to do at the very end of the lab. So you needed to calculate the mass of KNO3. So they got the mass of KNO3 and then the mass of water. And that's why if you do these calculations and you see that your water isn't right around 0.9 or 1 gram, if you've got like less than that, you got like a half of a gram of water or like you're over a gram of water, you have to take a look at that and say like, okay, I got some bad data here because you needed to have about 1 gram worth of water in order for this to work really well. Then you do a division, divide those two to get the mass ratio between the two of them. Then you need to multiply that by 100. Multiplying that by 100 gets you that solubility. And that's what you're going to graph along with the temperature at which that saturation happened. So what I did is I took that and since it's in the spreadsheet, let's go ahead and make a graph with that. So if you know how to do that, great. If not, it's not a big deal. So you don't want to have it be a column or a bar graph. You shoot for a scatter plot. That would be the better one to go for. So you can see that there's definitely a trend. So if you plot your points, your 6 points, and it doesn't kind of look like a curve like you saw on that first slide that we had from the notes. You got dots like up, down, all over the place. It looks like a big giant like the Himalayan mountains or something like that, you got some bad data. Still make your graph though. You still make that graph. You may not choose to use that to answer the questions though. I'm going to take this information, I'm going to put this on Canvas along with the pre-lab and the post-lab, so you can just use this graph in order to be able to answer the questions from the post-lab. Because if your graph looks really bad, don't use your graph to answer the questions. But still make a graph of your data though. You still need to do that. Does that make sense? Everybody okay with that? If you've already done the lab, and you made your graph, and you've done the questions, everything, and turned it in even, that's fine. I don't have a problem with that. We'll figure it out. We're not going to really penalize you for having really bad answers or really bad graph. Okay, so once you do that, there's one more thing I want to show you really quickly. It's kind of cool. It goes with this. We go to series here. Actually, I want to do legend. So I go to series. Down here at the bottom, there's this thing that says trend line. I'm going to click on that. And it automatically pops up a straight line. If you think your data is supposed to have a straight line. I'm looking at that. I don't see a lot of the data points falling right on the line. It looks like I might have about the same number above and below, so it's close. But I'm going to see if I got some other ones that will work better. So I'm going to switch my type. From linear, I'm going to try exponential. Try exponential. That one doesn't look that great either. So I'll try one more. Polynomial. Oh, that one looks pretty good. That line goes pretty much right on a lot of those data points. Only that one that's a little bit off. So I picked a bad one to use, I guess, with that one maybe. All right, but this will be on Canvas, so you can use this to answer the questions that go with the post lab. So just bring that up. You don't have to print this off and cut it out and glue it into your lab book. Just use it to answer the questions. That's all you really need to do. All right, then, if there's nothing else, please take out your iPad and put everything else away except your calculator, something to write with. Keep that little half sheet of paper for scratch paper. And you can have your orange survival guide card out. Your orange survival guide card for molar masses. Take out your iPad to take a minute quick. You like it? Can you put this away? Yep, you can put that away. Good morning.